This is the first of a series of 4 lessons on time. Your first reaction may be that this seems like rather a lot, and why do pilots need to know about time anyway? The 2 most practical reasons are that, firstly, you should know why different countries keep different times, and how to find what the standard time is in any country you may land in. Most laymen, and some pilots, when using the PA to passengers, call this the local time, but the correct term is standard time. Secondly, you need to be able to work out when it gets dark in different parts of the world at different times of the year, or when it gets light in the morning, especially if the destination airport does not have airfield lighting. These are good practical reasons. However, our measures of time are based on the Earth's rotation about its own axis, the Earth's rotation around the Sun, and the movement of the solar system in our galaxy. We therefore need to know something about elementary astronomy. The Earth is one of 8 major planets which orbit the Sun. We are going to look at the pattern of these orbits, because they affect how we define a day and a year. The laws governing orbits were worked out by Johann Kepler in the 17th century. Previously, it had been assumed that planetary orbits were circular, but this hypothesis did not tie in with actual observations. Kepler's first law is that the orbit of each planet is an ellipse, with the Sun at one of the foci. Let's start by explaining what an ellipse is and what these foci are. We'll begin with a circle. We define a circle by starting with the centre, then producing a radius of a constant length, and then we rotate the radius through a revolution. With an ellipse, we have 2 starting points, not 1. These are called foci, which we'll label F1 and F2. If the distance from F1 to the edge and back to F2 always stays the same, then by definition we have an ellipse. To make it a planetary orbit, we'll put the Sun at F1. F2 can now be ignored. As we now have an elliptical orbit, there will be a closest point of approach to the Sun and a furthest point. The near point is called perihelion. It comes from 2 Greek words, peri, meaning near, and helios, meaning sun. Perihelion occurs on or near the 4th of January. The average distance from the Sun to the Earth over the year is 93 million miles, or 150 million kilometres. However, at perihelion, that distance reduces to about 91.5 million miles. We do not use nautical miles when discussing distances in space. The furthest point is called aphelion. It occurs on or around the 3rd of July. At that point, the distance from the Earth to the Sun is at its maximum of about 94.5 million miles. In the Northern Hemisphere, early January can be one of the coldest times of the year, but this is the time when the Earth is closest to the Sun. The changing distance from the Earth to the Sun makes very little difference to the amount of heating, so the changes in the seasons must be caused by something else. We now move on to Kepler's second law. This describes how a planet's speed changes during its orbit. The orbital velocity is constantly changing with the distance from the Sun. It is fastest when near perihelion, and then slows down, reaching a minimum at aphelion. Kepler was the first person to find the relationship which describes how the speed changes. Kepler's second law is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. This is the radius vector. This is how far the Earth moves in a fixed time, such as a month, when near perihelion. However, when it is near aphelion, it is travelling slower. In the same time interval, the distance travelled round the orbit will be less. Kepler's second law states that if the grey shadings have the same area, the time will be the same. Let's remind ourselves of Kepler's first two laws. The first is that the orbit of each planet is an ellipse, with the Sun at one of the foci. And the second is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. Kepler's second law gives us a problem when it comes to explaining the length of a day. A day is one revolution of the Earth. We draw a line out into space from the centre of the Earth, passing through one particular meridian. As this line passes through some datum reference point, we call this meridian transit. Here we see a transit of the Sun. We start the clock. The Earth then rotates once until we have a second transit of the same meridian. We stop the clock, and the time taken is defined as 1 day. However, the length of our day will depend on what we take as our datum when measuring the transit. Remember that the Earth is orbiting whilst it rotates. We start off here, somewhere near perihelion, and will take some distant star as our datum. The distance can be regarded as being infinity for all practical purposes, so the light from it to the Earth is parallel, even though the Earth moves round its orbit. The Earth rotates once, and in that time moves a small amount round its orbit. It has turned through exactly 360 degrees with respect to space. This is called a sidereal day. However, what if we take the Sun as our datum? The Earth moves around its orbit. Therefore, if it rotates through precisely 360 degrees with respect to space, it will no longer be pointing at the Sun. In order to have a second transit with the Sun, it will need to rotate more than 360 degrees. In the time taken to make this extra turn, it will have travelled even further round its orbit. This is called an apparent solar day. Apparent is simply an astronomer's term, meaning that that's the way it appears to us. It is actually the true situation. An apparent solar day is always longer than a sidereal day. Now imagine the same situation somewhere near aphelion. The Earth would also have to rotate more than 360 degrees with respect to space in order to point back at the Sun. But because the orbital speed is slower, the time between successive solar transits is less than at perihelion. This difference in the length of an apparent solar day between perihelion and aphelion is half an hour. Over the year, the time between successive solar transits varies from about 23 3/4 hours to about 24 1/4 hours. This is nothing to do with changes in the hours of daylight and darkness, which is a separate problem. It actually means that the time from midday to midday, or midnight to midnight, changes over the year, if we take the Sun as our datum. What are the basic requirements for the length of a day to be useful to us? Basically, it should be related to the hours of daylight, so that 12 noon is always approximately halfway between sunrise and sunset. But it should also be of a constant length, so that an hour is always the same unit of time, whatever the time of the year. A sidereal day is of constant length. It always takes the Earth 23 hours and 56 minutes to turn through 360 degrees with respect to space. But it is not related to light and dark over the year. Suppose we are at perihelion. This is the meridian experiencing midday. If we use sidereal time 6 months later, that same meridian will now give us 12 noon on the clock, when it is actually the darkest period of the night. So clearly, a sidereal day does not meet the first of our requirements. It is not related to the hours of daylight.